All right, in this section we're going to be talking about definite integrals, means we're going to be not only finding the antiderivative of the integral, but we're going to figure out how do we evaluate that antiderivative between two given x values. And that's going to bring in what is called the second fundamental theorem of calculus, or FTC for short, is how I will typically abbreviate fundamental theorem of calculus. And the first fundamental theorem we will talk about a little bit later. Now, remember from the indefinite integrals video that the derivative of the area that you are finding is equal to f of x. And therefore, what we did is we took the antiderivative of both sides of our equation, and the antiderivative of the derivative gave us a, which is your area, and that area was equal to the antiderivative of f of x. And so we will refer to the antiderivative of f as capital F of x. So whenever you see this capital F, that's going to be referring to your antiderivative, evaluated at whatever value is given here. And so what we do is we've got this drawing or sketch over here. This is going to be our curve f of x. And if we put these x values of c, a, and b down here, these just represent constants that we can integrate between. Capital F of b, which means the antiderivative evaluated at b, is going to equal the integral from c to b. All right, so that means the green area is going to be referring to this area right here. It's that antiderivative, or if you remember, the antiderivative is going to be the same thing as your area. So the area from c to b is going to be referred to as the antiderivative evaluated at b. Now, the integral from c to a is going to be your antiderivative evaluated at a, and that will be your orange section. So the integral from c to a would be this area right here. All right. So that means that if we take the integral from c to b, which is our green area, and subtract the integral from c to a, which is the orange area, that would give us the integral from a to b. That would be this region right in here. So the green area minus the orange area is going to give us this region right here. And that area, that region, will be the integral from a to b of f of t dt. Now, this integral from c to b, as we see here, can also be written as capital F of b. And so that would give us capital F of b minus, and then this integral can be written as capital F of a. So minus capital F of a is equal to the integral from a to b of f of t dt. All right, so what is this really telling us? This is telling us that if I want to find an integral between two values, which again just means the area between this x value and this x value, if I want to find an integral between two values, that's going to be equal to the antiderivative of the function evaluated at the upper limit, b, minus that antiderivative evaluated at the lower limit, a. So there are some properties of integrals that you need to make sure that you know. This one we've already talked about before. It's just your power rule for integration. You can come over here to the right and look at this statement for a minute before we move on. If a function is greater than or equal to 0, which means you've got a graph that is above the x-axis. So let's say we've got this green function here between a and b. So a is going to be less than b. If your function is positive, which means above the x-axis, then the integral from a to b of that function is going to be a positive area. So if I want to calculate the area here, that area is going to be a positive area. Now, likewise, if you have a function that is below the x-axis, or f is negative, then that means that your area is going to be a negative area. So if you are integrating from a smaller value to a larger value and your function is above the x-axis, then that means you're going to be referring to a positive area. If you're integrating from a smaller value to a larger value and your function is below the x-axis or negative, that means that you are going to have a negative area. Now, that means that if we switch these limits of integration, then that would be equal to the opposite of switching them back. All right. So if I was to integrate from b to a, in other words, where this is your lower limit and this is your upper limit, this would end up being a negative area. Okay, so you'd have to put a negative in front of that integral. And then likewise, this one, if you integrate from b to a, you would have to put a negative in front of that integral. All right, so an integral from a to a just means that there's zero area involved here, because you're integrating between two x values that are the same value, and that's always going to come out to be 0. If you have a constant in front of your function, for example, if you had like 2x squared, that constant or coefficient can be brought out in front of the integral and then just evaluate what is remaining after that. This is kind of like what you would do with polynomials. For example, if you had x squared plus 2x, this property just simply means you can find the antiderivative or integral of the first term plus the integral of the second term. If there are 3 terms, you just find the integral of each term and add them together. And then this one says that if you take the integral from a to b, let's say we have this one over here and we extended this to c. All right, so on this, if you took the integral from a to b, which would be this area here, plus the integral from b to c, which would be this area, that would equal the integral from a to c, which would be the total area. That's what this this last property is saying here. All right, so let's actually work through some problems here. Starting with the first one, we have x over 2 plus 3. Let's take a look at it graphically and find the area geometrically, and then we'll do the calculus part of this. So this would be a line with a y-intercept of 3 and a slope of 1/2. And so just drawing our picture here. We are integrating from -2 to 4, which means we are integrating between here and here. So that would give us this area right here. Now, that is simply a trapezoid, which means we would find the area by taking base 1, which is 2, plus base 2, which is 1, 2, 3, 4, 5. Those are the two sides that are parallel to each other, multiplied by the height, which is the distance between the two bases, and that is 6, divided by 2, and that's going to come out to 21 as our area. So let's take a look at how we do this using our properties of integrals. And so this would be equal to the integral from -2 to 4. And this is the same thing as saying 1/2 x plus 3 dx. Now, if you take the integral of the first term, that would be the same thing as saying 1/2 times x squared over 2 plus the integral of the second term, which is 3x. And then we put a vertical bar, which means we are evaluating this between -2 and +4. All right, so just to simplify this a little bit, this would be x squared over 4 plus 3x between -2 and 4. Now, remember, these are your antiderivatives, or the antiderivative of this function right here. So to evaluate an integral, we evaluate the antiderivative at the upper limit of 4. And so that's going to be 4 squared is 16 divided by 4, plus 3 times 4, which is 12. And then we subtract the antiderivative evaluated at the lower limit, -2. So -2 squared is 4 over 4. Plus 3 times -2 would be -6. That's going to give us 4 plus 12 is 16, minus 1 minus 6, which is -5. Subtracting your negative gives us 21, which is the same area as what we found using this geometrically. All right, so take another one. We're going to do, again, both geometrically and using our calculus. So y equals -3 is simply a horizontal line at -3. We are evaluating this between 1 and 5, which simply gives us a rectangle whose area is 3 times 1, 2, 3, 4, which is 12. All right, so doing this using our calculus, the antiderivative of -3 is -3x, evaluated between 1 and 5. So we substitute, oh, by the way, this was a negative area here because this is below the x-axis. You can also think of this as having a height of -3. So that's a -12 for that area here. All right, so substituting the 5 in, -3 times 5 is -15, minus the lower limit, -3 times 1 is -3, and that gives us -15 plus 3, which is -12. All right, so the next one, we're going to branch off of our polynomials a little bit here. The antiderivative of sine of x is going to be negative cosine of x, and we're going to evaluate this between pi over 4 and pi, which would give us negative cosine of pi minus negative cosine of pi over 4, which would make this plus cosine of pi over 4. Negative, let's see, cosine of pi is -1, so -1 would be a +1. Cosine of pi over 4 would be √2 over 2. So your answer could be written this way. or as a single fraction would be 2 plus square root of 2 all over 2. Either way is okay on this. The next one, if you have 3 over x, let me do something incorrectly first to show you why it doesn't work, and then we'll show you how to do this correctly. If we try to do this as 3x to the negative 1, and you do an antiderivative of this, you would add 1 to your exponent, which would give you 0, and then you put this over that new denominator. Well, you see there's a problem here because you cannot divide by 0. So this is not the correct way to work this particular problem. Whenever you have a situation where your denominator is your variable raised to the first power, you are not going to convert it to a negative 1 power. Anytime you convert this to a negative 1 power, you're going to get that situation where you're dividing by 0. So what you want to recall on this is that this is equal to 3 times the integral from 1 to e of 1 over x dx, and you want to think about, well, what the derivative of what value or derivative of what function is going to give you 1 over x, and that is natural log of x. Now, one thing I want to point out on this, and let's look at this graphically for a second. 1 over x is a rational function that looks like this. Natural log of x is a function that looks like this. The domain of the original function of 1 over x is all real numbers except for 0, which means you can have negative numbers and you can have positive numbers, both, that will work in this function. However, natural log of x only works with positive numbers. So if you have a boundary here that includes a negative value, you would need to convert that to a positive value. And the way we do that is anytime you take an integral and it comes out to be natural log of something, you are always going to put absolute value bars around your x there. All right, so notice on these we are not putting the plus c, the plus the constant anymore. These are called definite integrals, which means we know exactly where the function is and we know what the value is going to be on these, and your plus c plus that random constant is not going to exist on this. All right, so now the next one, we want to recall the derivative of what is going to give us 1 over square root of 1 minus x squared, and that is sine inverse of x. And we're going to evaluate this between 1/2 and root 3 over 2. Now, most of the times they will tell you what the domain of your function is going to be. I'm just going to refer to the first quadrant right here. And so if we evaluate sine inverse of root 3 over 2 minus sine inverse of 1/2, this is asking what is the angle where the y value is root 3 over 2, and that is pi over 3, minus the y value, the angle where the y value is 1/2, and that is pi over 6. Now this would be the same thing as saying 2 pi over 6 minus 1 pi over 6, which will give us 1 pi over 6. Now the next problem, we do want to convert this one into an exponent, and this is going to be rewritten as 2x raised to the negative 1/2 dx. So to find the antiderivative, you're going to add 1 to your exponent, which will give you 1/2, divided by that new exponent, evaluated between 1 and 9. So cleaning this up a little bit, 2 divided by a half would be the same thing as 2 times 2 over 1, which is 4. Square root of x between 1 and 9. Substituting the upper limit in, you get 4 times the square root of 9, which is 12, minus 4 times the square root of 1, which is 4, and this comes out to 8 for your antiderivative. All right, so on this one, we're going to be looking at a graph instead of having a specific function. Our function is going to be given by this particular graph. All right, so the graph of a function f consists of a semicircle and 2 line segments as shown here. And we're going to let g of x equal the integral from 1 to x of f of t dt. So if I want to find the integral of g of 1, that means that g of 1 would equal the integral from 1 to 1 of f of t. And we know from our properties that if the lower limit and upper limit are the same value, your integral is 0. Find g of 3. That would equal the integral from 1 to 3 f of t dt. One of the reasons why I like this kind of problem is it reminds us that when we are doing integrals, what we are referring to is actually finding the area. So what we are doing here then is going to be finding the area between 1 and 3. We know that this part of the function is below the x-axis, which makes this a negative area. And because these are line segments, we can just simply look at this and calculate that area of a triangle, base times height divided by 2, and this comes out to be a -1 for this particular area. All right, so let's look at the next one then. The g of -1 would equal the integral from -1 to, positive 1 to -1 of f of t dt. Now when we do integrals, we want the lower limit to be the smaller value. And so what we're going to do then is we're going to switch our limits and put the -1 here, the positive 1 up here. But when we do that, that means we have to put the opposite sign or negative in front here. And so this would be the integral from -1 to positive 1 f of t dt. Now the integral from -1 to positive 1 would be the area right here. Now that is a quarter of a circle with a radius of 2. So that would be pi times the radius squared divided by 4, because it's a fourth of a circle, which will end up equaling pi. All right, so we have the same type of situation here, just a slightly different graph. This time it says that we just want to evaluate these integrals. So we're just going to get some practice doing that. The integral from 0 to 2 would be from here to here. And that area, well, we know that it's below the x-axis, which means it's going to make it a negative area. Again, this is a quarter of a circle, so pi times the radius squared divided by 4, because it's a fourth of a circle, giving us negative pi for that area. All right, so the next one says the integral from 2 to 6. Well, that's going to be the area of this triangle right here. We see that this is above the x-axis, so it's a positive area. The base of that triangle is 4. The height of the triangle is 2, and divided by 2. Base times height divided by 2 is going to give us an area of 4. And then the last one here on this page is the integral from -4 to positive 2. So that's going to be the area here plus this area. So we need to break this off into two sections. The first section is a triangle. It also is a negative area. The base is 2 times the height of 1 divided by 2. And then we have the semicircle, which is below the x-axis, so it's a negative area, minus pi times the radius squared divided by 2 because it's half of a circle. And this comes out to -1 minus 2 pi for our area. All right, we're just continuing the same graph with a few different problems here. So the next one is the integral from -4 to 6. So that would be this area plus this area plus this area. All right, well, we already know the integral from -4 to 2. That was in the previous problem. And so if we take that area plus the area from 2 to 6, we can add those together. So the first area was -1 minus 2 pi plus, and then the area here is from, let's see, 4 times 2 divided by 2, that's plus 4. That'll give us a total area of 3 minus 2 pi. Okay. Now the next problem says absolute value, which, if you recall, absolute value takes whatever is inside, makes it positive. So that means these negative areas become positive areas here and here. Anything that's already positive just simply stays positive. All right, so that means this would be -1 plus, I'm sorry, this will be a positive 1 now. This would be a positive 2 pi. And so the area would come out to 1 plus 2 pi plus 4, giving you 4 plus 2 pi for the integral of the absolute value of f of x. So again, absolute value just takes whatever those areas were that were negative and turns them into positive areas. All right, so then the next one here is the integral from -4 to 6 of f of x plus 2 dx. You have to be careful on here. The tendency for a lot of people is just to say, oh, the integral from here to here of f of x, well, that was this value here, 3 minus 2 pi. So the tendency is people will just say, let's add 2 to that value. That is not what this integral is saying to do. We need to write this integral as two separate things. So this would be the integral from -4 to 6 of f of x dx plus the integral from -4 to 6 of 2 dx. That's using that property where you are actually taking the integral of both terms. Now this first integral right here, that is the value that we had right here. And so we are going to end up with 3 minus 2 pi for that part. However, we are not just adding 2 to this. The integral of 2 is 2x. And then we need to evaluate that between -4 and 6. And so 2 times 6 would be 12 minus 2 times -4 is -8, giving us a total of 20. So we are not adding 2 to this value, we are adding 20. So the integral would be 23 minus 2 pi.